بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. أعزائي الطلاب, today we have the density. The main objective today, we want to measure the density for different objects, solids and liquids. And in the end of the day, we will use Archimedes principle to measure the density of unknown object or irregular object. You know that there is simple formula for the density. The density equals the mass of the object divided by the volume, and the unit will be in kilogram per cubic meter. Now, in exercise number 1, the main objective, we want to measure the densities for different solids. What we having there, we will have 3 objects. We will have this aluminum object, and we will have this brass object, and we will have this plexiglass object. We want to measure the density by using the geometry and by using this formula. This formula depends on the mass. The mass can easily measure by using a balance for all objects, and the volume, if we have geometry, we can easily find the volume of the object. Our object in cylindrical shape, we can measure the density of this object by knowing the height and knowing the radius of that object. Then this is the main objective in the first exercise. We will have different objects. The first object is brass. The second one is aluminum. The third object is plexiglass object. We can measure the mass by using the balance in kilogram. Accordingly, we can measure the radius of the object by using the diameter, and this is in meter. Then we can find what is the radius also in meter for this object, and also we can measure the height of the object. Then we can calculate the volume in cubic meter, and we can measure by knowing the volume and the mass, substituting this formula, we can measure the density of this object, and we call this density experimental value. And by knowing the theoretical value or accurate value for these densities, we can also end with some percent error in our work, in this experimental work, by using the well-known formula for percent difference, which equal the absolute value of theoretical value minus experimental value divided by theoretical value multiplied by 100. Now, about the densities for these objects, we know that the density of the brass is equal. The density of the brass equal to 8.4. The brass is 8,400 kilogram per cubic meter, and for the aluminum it is 2,700 kilogram per cubic meter, and for the aluminum or plexiglass it is 1,180 gram per cubic meter. Now for exercise 1, to measure the mass for this object, which is brass object, we put it in the balance to measure its mass. The mass of this one is 325 gram point 3, and also we need to know the height of that object. We'll use a vernier caliper. It should be 0 where nothing there between the caliper of that apparatus. Now this is the height, which equal to 198.4, and this is in part of millimeter, which is 19 millimeter point 85. And the diameter of this object is 4 centimeter point 9881, or 49 millimeter point 83 by using this vernier caliper. Now we know the height, we know the diameter, which will lead for the radius, and we know the mass. We can use the simple formula, density equal mass divided by the volume. We'll do the same thing for the aluminum, and also we'll do the same thing for the plexiglass object. For these three objects, we will provide you in the template with the data for the masses and the values of the height and the value of the diameters. And we will give a different version for different students. In this part, exercise number 2, the main objective here, we want to measure the densities for liquids. We have water here in this cylinder, and we have this unknown oil. We want to measure the density for these liquids. As we state in the first formula, we should know the masses and we should know the volume. But here we will use this graduate cylinder. This graduate cylinder gives us the height here. But the height here is dimension in volume because it is measuring the value in milliliter. And the converging factor, we have 1 milliliter equivalent to 1 cubic centimeter, which equivalent to 1 multiplied by 10 to the power minus 6 of the SI unit of the volume cubic meter. Is in each reading in millimeter in these cylindrical tubes, it will give us the value of the volume of the object. Then we can use this formula, the density equal a mass multiplied by the volume. Isn't the only problem we have with the fluids is how to find the volume of the fluids, and we can easily find the volume by using this graduated cylinder. To do that experimentally, we will measure the mass. What do we need? We need the mass. In the case of the water, we need the mass of the oil and the volume of the oil. For the case of the water, we need the mass of the water and divided over the volume of the water. Then what do we need? We need to find the masses. In the first, we will have empty one, and we measure the mass for the empty one, and then we will measure the mass with for the one which filled by the water. Then after that, we will measure the mass for the one which filled by the oil. Then what we will have the mass of the liquid, mass, water or oil, multiplied by cylinder. We can use the balance to measure them, and we call this M2, and we will measure the empty one. We will use the balance, we will find it equal to 0.1490 of kilogram. Accordingly, we can measure the mass of the liquid, which equals the value of M2 minus M1 in the case of the water, and M2 here minus M1 in the case of the oil. We need also to measure the volume, the height of the water, and the height of the oil, which reflecting by using this graduated cylinder. It will give us the volume of the oil and the volume of the water. We can measure them by using this indicator here and put it in solid place like this, and we can easily take the reading of the water. By the same way also, we can measure the height also of the oil and take the reading from the graduated cylinder there. And I will write the reading for these values now on the board. Now, in the third part of this experiment, the main objective, we want to use the U-tube, and this U-tube will help us also to find the density for unknown liquid. What we will do, we will put water in the U-tube, then after that we'll put oil from one side, then the oil, because it is less in density, it will suspend on the water, and it will be higher than the water. This side will be the oil side, and this side will be the water side. Now, at the interface between the oil and the water, we will use something very important there. Pascal principle telling us the pressure should be always equal at any side inside any tube. Now we have this tube here, and we have in the both sides we have something pressuring these points. Let me call these points A and these points B, and according to Pascal principle, any points at the same height will having the same pressure. That means the pressure at point B is equal the pressure at point A. Listen, what we have pressure at point A, this is the starting, should equal the pressure at point B. Now the pressure which comes from point A is the air column to infinity plus the amount of the water between these points and the surface of the water. And this equal the ambient pressure, which equal 1 multiplied by 10 to the power 5, plus the amount of the water which making pressure at this point, which equal the force over the area, because the pressure always equal the force divided by area. This at point A should equal also the same thing. The pressure at this point comes from the ambient pressure, the infinity column, the air, infinity column of the air amount there, plus the pressure which come from this height of the oil. This is the ambient pressure, which equal, as I mentioned, 1 multiplied by 10 to the power 5 Newton per square meter, plus the force which come from the oil, which is force divided by area at the point B, which is oil. Now we can eliminate this from both sides because it is open tube. Accordingly, we know that the force equal mass multiplied by gravity, then the mass multiplied by gravity divided by area at point A should equal mass multiplied by gravity divided by area, where at the other point B, and we can also eliminate the G. And we know that the mass equal the density multiplied by the volume. We can put density multiplied by the volume divided by the area should equal, this is at point A, should equal density multiplied by volume divided by the area, and this is at point B. And we know that the volume of any cylindrical shape equal the area of the base multiplied by the height. I will take out this volume, and write instead of it the volume, which is the area of the base, multiplied by the height, and we can eliminate A with A. This is at point A, should equal density multiplied by area multiplied by height divided by the area. Also we can eliminate A from both sides, and this is at point B. Now let me simplify this equation and customize it with our YouTube there. At point A we having water. Then this density is, let me start at point B. At point B, this is the density of the water. This is the density of the oil, multiplied by the height of the oil divided by nothing. Should equal to the density of the water multiplied by the height of the water. Accordingly, we can catch our unknown. Our target here is what is the density of the unknown liquid there, which is oil, equal the density of the water multiplied by the height of the water divided by the height of the oil. This formula will be used to find the unknown density for any liquid we put it in that side of this YouTube. If we put oil, then the density of that unknown, the unknown density of this oil equal the density of the water, which is well known, 1000 kilogram per cubic meter, 1000 gram per cubic meter, and the height of the oil is, the height of the water is this height, and the height of the oil is this height. This is the height of the oil, and this is the height of the water. To find that, we will call some distance here. We will make this reference as YB. This will be our YB. and this will be Y of the water, we call it in the experimental word, and this will be the Y of the oil. We measure this from the reference points here to here, and we measure this from here to here. If we know this some value 10 centimeter or something like that, and if this is 10 centimeter and this is 17 centimeter, that means this YH, height of the water, equal YB minus Y water minus YB. The same thing it will be also for the oil, Y of the oil minus reference points. It will give us the value of the height of the oil. Let me make this reference. Let me make this reference or any other reference, because we will subtract the value of Y for all these values. Accordingly, the YB will be this distance, and the YO will be exactly this distance. Isn't if I know this one and I know this one, I can find this one, which is height of the water. If I know now the same thing, the Y for the oil, and I know this height, I can get this value, which is the height of the oil. Now this is the YouTube. We have it in explanation. This is the water side, and this is the oil side, and you can see here this is the interface between the oil and the water. And this point we will call it, this will be our zero here down, our reference, and we will call zero reference, zero value, and the Y reference will be here, we call it YB. This is the interface point, we call it YB, and we take the reading from here, and we will put the value on the board. It's about 0.08 centimeter if we take reference points, and we will take the reading from here. This is the Y of the water, and the reading from here will give us the Y of the oil. I put this value on the board there. This is the Y of the oil, 29 centimeter point 1, and the height of the water, 27.4 centimeter, and the height of the reference point, 8 centimeter from some reference value. Accordingly, you can measure the height of the water. This will be the height of the water, the difference between Y, sorry, this is oil. This is the height of the oil equal the Y of the oil minus the reference point, and this is the height of the water, which is Y of the water minus the value of the reference value. The values are here. You can easily find what is the height of the water. Accordingly, you can measure the density of the oil, and you can measure the percent difference also in the oil. Also, you have to add here the height of the oil. You can measure this value and this value, and then you can find the density of the oil. The density of the oil equal the density of the water. Take it 1,000 kilogram per cubic meter and multiply it by HW divided by H of the oil. Now we got two values. We got two values of the oil density. We got two values of the density for the oil. One from exercise number 3 and one from exercise number 1. We can easily find the percent difference in any work in exercise 1 or 2 or 3 equal the experimental value minus the accept value or critical value divided by the accept value multiplied by 100. It is the absolute value of experimental value minus measured value or critical value divided by the most important thing is divide on what? Divide on the accurate one, the measured, the theoretical or the acceptance value. For this exercise, both of them in the value of density of the oil in exercise 3 and 2, both of them are experimental. You have to divide on the biggest one and find the percent difference in exercise 3, like what you have done in exercise 2 and in exercise 1. Now suppose we have a regular object like this. Composed from different material, plexiglass plus some material, metallic material inside, and also the hanger itself from other material. And we cannot have geometry to find formula for finding the volume of this object. How to find the density for irregular? We call this irregular object. To find the density for irregular objects, we will use Archimedes principle. Archimedes principle telling us if we have any object and we totally merge or submerge that object under surface of fluids, it will experience an upward force. This force we call it point force. It is pushing the object upward, and this force equal the weight of the replaced fluids. Now when we put this object inside this fluid, this object having weight, we call it W. Now the weight of that object will appear at now we call it apparent weight, because there is pushing force in the upward according to Archimedes principle, and this point force equal the weight of the replaced fluids. If we follow these dash points, this dash object as water or as fluid there, and we weight it, the weight of that dash object will equal the amount of the point force. Then we can summarize this: the point force equal the weight, the real weight of the object minus the apparent weight. Okay, the weight, this point force equal the weight minus the apparent weight. This is the weight if we are in a vacuum, and we regularly consider our fluid air as vacuum, because the point force will be very small because the density of the air is very small. This point force equal the weight minus the apparent weight. And according to what Archimedes states, and this equal to the M minus M apparent multiply, I will write it in the format of the mass to only eliminate the G, and this equal to what? This equal to the weight of this dashed line, the weight of the replaced fluid. And we know that the weight of this replaced fluid, equal to what? Equal to G multiplied by the mass of this replaced fluid. I'll make now this equal to that, and I eliminate G from both sides. Accordingly, we know that from the well-known formula for the density equal mass divided by volume. The mass of this dashed line, which is replaced water or replaced fluid, equal the density of this replaced fluid multiplied by the volume of this replaced fluid, which is the volume of the water, which is the same volume of the object. The volume of this dashed line is the volume of the water, which is replaced by that object. And it is always equal to the volume of what? Of the object itself. Then this density of the replaced fluids, if we use the water, this we can replace it by water. Then we can make it similar here. The density of the water, this point force, equal, I already eliminated G. This term should be multiplied. If I talk about force, this should be multiplied by G if we're talking about force. But however, this point force equal the density of the water multiplied by the volume of the object. And I know the volume of the object is what? Is the density of the object, multiplied by, the volume of the object is what? Is the mass of the object, divided by the density of the object. I call it here O, this is object. What's our target? Our target is to find the mass, the density of this unknown object. It starts appearing here. Now I put this in the numerator there. This will give us the density of this object should equal the density of the water multiplied by the mass, this side as is, and I take this that side, and I will take this M minus M apparent in the denominator here, M minus M apparent. Is in this formula, this is the formula which will be used experimentally to measure the density for any any unknown object by using Archimedes principle, which equal to the density of the fluids there, in our case will be water, multiplied by the mass minus divided by the mass minus my apparent. What is the difference between mass minus my apparent? The mass is the mass in the vacuum or in the air, if you consider air as a vacuum. And the mass apparent is the mass when we place the object under the surface of the fluid in the experiment. Now we have here Archimedes principle. We have the balance. By this side of the balance, we can measure the regular weight, the regular mass. And when we hang it and put it inside the fluid, which is water here, we can measure the apparent weight. We have the aluminum, the brass, and the plexiglass, and the irregular. In the beginning, we have to be sure that the balance indicator is in the 0, while there is nothing. We can adjust the balance to be in the 0 level from this screw here, from this knob here. Now we have this aluminum, we put it on this side of the balance, and we want to measure the mass of that object. It is 100 gram. It is 110. It seems that it is less than 10. 100 gram. 100 gram and 9 gram. Point 9, which is 100 gram. 0.99. Also we can measure, but we can take another object also, measure the mass of that object. Now this one, it is about 109 gram, 0.3, and also we can hang the object by this string and immerse it inside this fluid. It shouldn't touch the wall of the container there. And we find the weight is less than that weight. It is about less than this. This is 50. This is 60 gram. Let's check. 60. It is almost 68, 67. More than 67. Yeah, it is about 68.6 gram. This is the amount of the mass. We call it apparent mass because it is under the surface of fluid. It is totally immersed in that fluid. The same thing we'll do it for the brass. We will measure the mass by this side of balance. Then plexiglass will measure the mass. I'll put the values there in the board. And also I will measure the mass for the plexiglass by the same method. Then after finishing taking the reading from this side, this is 40 gram, 48 gram, less than 48. Now the indicators go to the 0 level. It is 40 gram plus 6.5. It is 46.5, and then it here gram. The same thing, we put it under the surface of the fluids, and we will measure the amount of the mass from the reading of the balance here. It is more than 10 gram. It seems to be 13 gram. Now the indicator now go to the 0 level. It is 10 gram plus 4 gram point 0.3, which is 14 gram 0.3. Now I will put these data on the board on the table there.